Alright, so in this video we should be closing out our preliminary discussion of solvability. And we're going to start out with solvability criterion. And it starts out with a lemma. We let X be an endomorphism of a finite dimensional vector space V, and S or N be its semi-simple or alternatively nilpotent component. We then let the adjoint representation of X the adjoint representation of S and adjoint representation of N be in the general linear Lie algebra of V. Then the adjoint of S, adjoint of N is the semi-simple alternatively it's nilpotent component of the adjoint of X and is equal to a polynomial in ad of X with coefficients in K and no constant term. And let's prove this. Now we know that we definitionally can split the adjoint of X into the adjoint of S plus the adjoint of N. With the bracket of the adjoint of S and the adjoint of N being 0, so the adjoints commute, and that the adjoint of N is itself nilpotent. So we will show that adjoint of S is semi-simple and we have, without loss of generality, let K be algebraically closed. Now we're going to let EI from 1 to n be a basis of V such that S of EI is equal to just lambda I EI. So we're essentially diagonalizing our S. Now we let capital EIJ be the canonical basis of the n by n matrices on K, which is the equal to the general linear Lie algebra of V. And then, by the formula we saw before, the adjoint of S on E of IJ is equal to lambda I minus lambda J acting on each E of IJ. Hence, the adjoint of S is semi-simple. And we're done with that. Another lemma here. Let M be a finite dimensional vector space. And then we're going to let A and B be two vector subspaces of the general linear Lie algebra of M, such that B is inside of A and we let T be the set of T in the general linear Lie algebra of M matrices on M, such that the bracket of T on all of A is inside of B. If Z is in T, such that the trace of ZU is 0 for all U and T, then Z is nilpotent. Now proof. Once again, we're assuming K is algebraically closed. Let S and N be the semi-simple and nilpotent components of Z. And we're going to let E to the I be a basis of M such that S on E of I is equal to lambda I E of I once again. Under V and K, V and K, which is algebraically closed, be the vector space over Q for the rationals generated by our lambda I. So now we need that V is just nothing. So let F be a rational linear form on V I'm going to let T be the endomorphism of M such that T of each EI is equal to F of lambda I times EI. If EIJ is the canonical basis of GL of M, as we saw before, defined by matrix EIJ on an element of M, determined by the basis K is delta JK E of I, so EIJ just sends EJ to EI, and everything else is 0, so that's easy enough to understand. Then the adjoint of S on EIJ is equal to lambda I minus lambda J of EIJ, as we saw before. And the adjoint of T on EIJ is going to be, remember T is defined through, based on a Q linear form F. Don't know why I was struggling for that so hard. F lambda J EIJ. Exists a polynomial P with no constant term and coefficients in K such that P lambda I minus lambda J is equal to F lambda I minus F lambda J for all I and J. Then we have that the adjoint of T is equal to the polynomial P acting on the adjoint of S. Also, the adjoint of S is a polynomial with no constant term in the adjoint of Z. Now, let me check real quick. We have that the adjoint of Z on an A is inside of B. I just want to check over everything. Whence the adjoint of T on A is definitionally in B, because we had T the set of GL of M. Yeah. And this is a different T, but you get it. Now we get, and 0 is the trace of Z on T, which is the sum of lambda I f of lambda I, so that 0 is equal to f of the trace of zt equals to the sum of f of lambda I squared. So f must be equal to 0. All right. Next theorem. This is also known as Cartan's criterion. So we're going to let G be a Lie algebra M a finite dimensional vector space, rho a representation of G on M, and beta the bilinear form on G associated with rho. Then rho of G is solvable if and only if the derived algebra of G is orthogonal to G with respect to our bilinear form of beta. Once again, without loss of generality, let G be a subalgebra of the general linear Lie algebra of M. This is a subalgebra, and rho the identity. If G is solvable, then the derived algebra of G is contained in the largest nilpotency ideal of the identity rho with respect to beta. Now, we're going to suppose the derived algebra of G is orthogonal to G with respect to beta. We show that G is solvable. Let T be the set of elements T in the general linear Lie algebra of M such that their action on all of G sends G into dg. If we have some element T and T and X and Y in our group, then we have that the bracket of T and X must be within the derived algebra, so the trace of T times the bracket of X and Y is equal to, we know it's equal to the bilinear form of T on X with Y, but this just sends to the left element is in the derived algebra, which is by assumption orthogonal to G, which is in Y, which holds Y. So this has to be 0. So by linearity, the trace of TU is equal to 0 for all U in the derived algebra of G. As we have that derived algebra of G, every element of the derived algebra of G is definite. We're going to meet the definition of T pretty easily. We have that every X in the derived algebra of G is nilpotent. So the derived algebra itself is nilpotent. So, as we saw last time with their corollaries, G is solvable. And there we go. Now, next section is further properties of the radical. And once again, we start out with a proposition. I don't know if we actually did that last time, but we're doing this time. Let G be a Lie algebra with a radical R. If rho is a finite dimensional representation of G, with a bilinear form beta, then the radical and the derived algebra of G are orthogonal with respect to beta. B says that R and the derived algebra of G are orthogonal with respect to the killing form. Proof that x and y be in G, z in R. Then the bracket of y and z is in the intersection of the G and R, hence beta of xy as bracket of x and y and z. We can freely move over that bracket and then we had by our first theorem of the semi-simple or the solvable, whatever we're dealing with here, which is solvable, this is going to be 0. So that's A down. R prime be the orthogonal of dg with respect to the killing form. It is clearly an ideal. Containing R. As the image of S under the image S of R prime under the adjoint representation of G this image S is solvable by our second theorem from this unit. Hence, R prime is solvable. I guess we don't need this hence since we have the as. R prime is solvable as a central extension of S, giving us that R prime is contained within R. We have some corollaries, as you do. Let G is going to be a Lie algebra. Then G is solvable. If and only if dg is orthogonal to G with respect to the killing form. And we've already proven this one up in above. Second corollary. The radical R of G as above is a characteristic ideal, which, as recall, means it is invariant under arbitrary derivations and not just inner derivations, which are just adjoint representations. Now we have seen that the derived series of G is a characteristic ideal, and that the killing form is a characteristic ideal. Hence, R being the orthogonal of dg, being in the orthogonal of dg at least, with respect to the killing form. I think it is the orthogonal, right? I am not processing anything right now. Is a characteristic ideal. Yeah, we did have that R is orthogonal of G, of dg with respect to the killing form. Okay. Third corollary, let G R is above and A is an ideal of G. Then the radical of A is equal to R intersection A. Proof. R intersect A is a solvable ideal of A. And so it is contained in the radical of A, which we're going to call R prime. Conversely, R prime is an ideal of G. So R prime is within R. And we're done that. Now, our previous result, which says that the radical is a characteristic ideal, can be expanded on now with a proposition stating that we let GR as above and N be the largest nopotent ideal of G. each derivation of G maps R into N. Our proof. So we're going to let G prime be the sum of G plus Kx naught be a Lie algebra in which G is an ideal. We see it's of codimension 1 such that the derivation of x, our arbitrary derivation, is equal to the bracket of xo and x. This is a trick we've seen before for all x in G. Essentially, we can create we just add a dimension onto our Lie algebra so that our derivation we're trying to study becomes an inner derivation. We have from a previous result that R is contained in the radical R prime of G prime then we have, I'm just on here so I can get to another line, that derivation on the radical is the adjoint of x naught on the radical, which is contained in the intersection of the derived algebra of G prime and the radical of G prime, which is equal to S prime, is what we're going to call this. As you'd expect, for all x in S prime, the G prime adjoint of x is nilpotent. Once again, from our first theorem of solvable algebras. Hence, for all x in the intersection of S prime and G, the G adjoint of x is nilpotent. Hence, d of r is in the nilpotent ideal S prime intersect G of G. We have one last corollary for this section, and then one last section for this unit, I guess. Corollary is that the largest nilpotent ideal of a Lie algebra that is not readable algebra is a characteristic ideal. And the proof, no, that's a corollary. So, remark. With R the radical of some G, N being the largest nilpotent ideal of some G, S being the nilpotent radical of G, and T being the orthogonal of G with respect to the killing form. As above, I don't think we specified before T the orthogonal of G with respect to the killing form. We have a size comparison here. The radical of the G is the largest. Inside of that is the orthogonal of G with respect to the killing form. Inside of that is the largest nilpotent ideal. Inside of that is the nilpotent radical. And all of these have been shown individually before. Now, there's one last chapter, gonna be a shorter one. It's Bourbaki, so you know what this is gonna be. We're gonna be looking at extension of the base field. And this will be the last topic for solvable algebras. GBA Lie K algebra and K1 an extension of K. GK1 is solvable if and only if G is solvable since, if you recall, our original definition of solvable is that the derived series terminates and the extension of the nth derived series, the nth derived algebra of the extension of G is the extension of the nth derived algebra of G. So that's pretty easy to follow. So we're going to let R be the radical of G. Then the extension of the radical is the radical of the extension. How do we know this? We're going to let beta be the killing form of G, as R is orthogonal is rather the orthogonal of the derived series of G with respect to the killing form. The extension of the radical is the orthogonal of the derived series of K1. Keep in mind it doesn't matter whether or not we extend G first or we're extending G or its derived series. And R, the extension of the radical is the orthogonal of the extension of the derived series with respect to the extension of the killing form. And because of our proposition, which we showed before, we are done. And with that, I believe we are done with nilpotent algebras. Once again, I'm going to take a moment at the end of the chapter to cross-verify with other books. Oh man, okay. So, I'm looking through. I see we once again have the extension, the analog of Lee's theorem, in this case, to the group version. And I don't know if we'll have anything else in my other book here, which of course tackles solvable first. And yeah, they're not going to say anything new here. They're not going to cover Lee's theorem until they don't even cover the killing form. Okay. Sorry, this is always the weird part of videos, but I gotta like that's the Casimir. I'm gonna have to go through Humphrey separately. Is it worth it going through the group theoretic analog of Lee's theorem? That's, I think it's long enough. It's probably going to end up being its own video, actually. It's a full 2 pages. So maybe we're not done quite with, I mean, we are done with, solvable algebras. We're just going to be covering, I guess, solvable groups next time, briefly. Maybe.